Howdy, and welcome to Mean 410, Mean 689, Internal Combustion Engines, Advanced Internal Combustion Engines, Thermodynamics Refresher. So, basically what this refresher is meant to do is just to remind you of some of the core principles that you would have learned in your thermodynamics course and how they specifically relate to how we use them in analyzing internal combustion engines. So it's somewhat of a general discussion, right? I basically am discussing things in terms of general thermodynamics, but I'll point out some specific features as to where we'll use this information in the context of internal combustion engines. Also, everything that we're talking about in this refresher is stuff that you'll need to know or conceptually understand in order to apply the equations that we use with internal combustion engines. Okay, so to get started, first of all, what we recall is that we have definitions for what we call a system and what we call surroundings. Okay, so real quickly, let me just define these for you. Okay, what we define as the system is a region or area of space that we apply governing equations to. It's the region and space that we're interested in. Okay. For example, when doing IC engine thermodynamic analysis, the system may be taken to mean the entire engine or just one cylinder of the engine. Okay. You'll actually see us do that frequently. You'll see us go between defining the thermodynamic system to be the entire engine or being just a cylinder of the engine, right? And, of course, we typically call system, we'll use words like control system, control volume, control mass, right? So words such as control system, this is what we would say is the most general term. Control volume, referring to a fixed volume in space. And control mass, which refers to a fixed mass in space, all are various terms for the word system. Okay, so if you hear me say control system, control volume, control mass, this is all referring to the thermodynamic system of interest. Okay, now every thermodynamic system, unless it's isolated, and we don't need to get into these real nuanced details, but every thermodynamic system is likely going to be interacting with what we call the surroundings. Okay, so the surroundings are the regions of space outside of, but typically interacting with, the system. Okay, so for example, systems will often transfer mass, energy, and entropy, or I should say will often exchange mass, energy, and entropy with the surroundings. Okay. Generally, the surroundings are not analyzed using our governing equations. They simply act as a receiver or provider of mass, energy, and or entropy to the system. Okay, getting back to that idea that the system will exchange mass, energy, and entropy with the surroundings. That's really all that the surroundings do, is they basically act as a region of space that either supplies mass, energy, and entropy or accepts mass, energy, and entropy from the system. Okay? Okay, so in the case of IC engines, if the entire system, that is the whole engine, is taken as the control system, then the surroundings would be the space near the engine, right? So for example, the atmospheric air, okay? If instead we take one cylinder as the control system, then the surroundings might be engine coolant or different metals near and around the cylinder. Okay, so it all depends, right? It all depends on what you're defining as your system and your surroundings, but it's important to understand these two basic definitions. So when we return to these handwritten notes that I have, when we talk about a specific system, we can basically have three types of systems. We can have what is called a closed system, we can have what is called an open system, and we can have what is called an isolated system. I have definitions for closed and open. We will never deal with isolated systems here in IC engines in 410. Isolated systems are really just a fundamental construction for being able to define equilibrium of a system. And so I probably would have talked about that if you had me for 315, or we talk about that if you take advanced engineering thermodynamics, which is mean 615, the graduate level thermodynamics. But for the purposes of IC engines, what we really need to understand is the difference between a closed system and an open system. And this is not complex, right? So if it feels like I'm overcomplicating this, don't let that cloud your current understanding of it. A closed system is really just a system, a control system, right, that only allows energy and entropy exchange with the surroundings. That is, there is no mass exchange with the surroundings for a closed system. Okay, it can still transfer energy, which is usually in the form of heat and work transfer, and we also need to add that a closed system can transfer entropy, which would which would only be in the form, well, could either be in the form of heat transfer or work transfer, or not work transfer, excuse me, entropy generation. So let me capture this real quickly, right? So a closed system can also transfer entropy in the form of either heat transfer or entropy generation. Note that entropy is not transferred with work transfer, right? That is, one of the fundamental bases is how we separate work transfer from heat transfer is heat transfer is entropy, right? Heat transfer is thermal energy, it's disordered energy, if you will. Whereas work energy is energy without entropy, right? It's ordered energy. It's energy that's all going in one direction, right? So work energy does not possess, if you will, entropy. Okay, mechanical energy doesn't possess entropy, whereas thermal energy does possess entropy. Okay, so that's our definition of a closed system, and we can also define an open system, right? Before I do that, though, let me give you a common example, right, of where we see a closed system, particularly, of course, in an internal combustion engine, particularly, of course, a reciprocating piston cylinder internal combustion engine. So this space that gets formed, once the intake valves are closed and the exhaust valves are closed, you, of course, have a closed system that's bounded by your piston on the bottom, your cylinder liner on the sides, and your cylinder head at the top, right? So there's no mass transfer, at least ideally, there are no mass transfers within this system. We can effectively call this region in space here a closed system, okay? Now, when you have a closed system, and all of a sudden now your region of space becomes a fixed amount of mass, right? In other words, the mass can't change within this system, so we inherently typically call closed systems control masses. In other words, it's the region of mass, it's that mass that we're interested in analyzing, not so much the region in space. Okay, we're analyzing that fixed amount of mass when we do closed system analysis. Okay, so now that we've defined what a closed system is, we can proceed to define what our governing equation for a closed system is. We'll come to an open system in just a little bit, okay? And so when we look at the various ways that the energy can change, so this du term here, that's the change in internal energy, okay? The energy of this control system, of this closed system, can change by either transferring thermal energy or transferring work energy, okay? Now, a little bit later on, we're also going to learn that the energy of this system can change form in the sense of being able to go from reactants to products. So, for example, in a combustion process, this control system will consist of reactants, fuel and air. And a reaction will take place where those reactants go to products. And in doing so, the properties of the control system will necessarily change because you're changing the species from reactants to products. Interestingly, and we'll come back to this later on in the semester, the energy of that system does not change, assuming that there is no heat transfer or work transfer in that combustion process. Okay? Other properties do, of course, change, though, as you change your species from reactants to products, and we'll come back to that again later on in the semester. So for your typical closed system, these are your three energy terms. You have change in energy of the control system itself, that's dU. We have delta Q, which is heat transfer, and we have delta W, which is the work transfer. Notice that this U here is written in lowercase. What that means is that it's the change in the specific internal energy, right? So if you remember, we write properties in thermodynamics as either lowercase or uppercase. So dU, for example, is the change in total internal energy of a control system. And because it's, as a capital letter, it's the change in total energy, then we would call that, or we would have units of kilojoules, okay? Likewise, we can have d little u, which is the change in specific internal energy of a control system, and this has units of kilojoules per kilogram, okay? The other terms, this delta Q, so just a little bit easier for me to type out delta rather than write it out, this is the differential change in heat transfer. Because the Q is capital, that would have units of kilojoules, not kilojoules per kilogram. And then, of course, we also have written there delta W, which is the differential change in work transfer. And because it's written as a capital W, this would be units of kilojoules, not kilojoules per kilogram. For a closed system, you can write delta little q, which is the differential change in the specific heat transfer, so it would have units of kilojoules per kilogram. Likewise, you can have delta little w, which is the differential change in specific work transfer, which will also have units of kilojoules per kilogram. Okay, so the first law of thermodynamics, of course, says that energy is conserved. So the change in energy of the control system, this du, has to be balanced by energy that flows in and energy that flows out. So when we write the first law and when we draw our general control system, our general thermodynamic system, we typically write heat transfer into the system to be positive and work transfer out of the system to be positive, okay? The way that we rectify that, though, because this is, in fact, an energy in, which is positive, and this is an energy out, which is negative, we introduce a minus sign in our first law equation to account for this positive orientation of work transfer. That work transfer out of the control system is taken to be positive. So our first law equation for the closed system basically says the following. The change in energy due to heat transfer, so the heat transfer that's added, minus the work transfer is equal to the change in energy of the system, du. So delta Q minus delta W is equal to du. In words, it means that heat transfer minus work transfer is equal to the change in system energy, okay, the change in the energy of the system. Now, one thing that you'll note is that what we've done here is we've neglected kinetic and potential energy. If we were not neglecting kinetic and potential energy, then we would have du plus 1/2 mv squared, that'd be the change in kinetic energy part, plus delta mgh, which would be the change in potential energy part. We very rarely, if ever, need to account for changes in kinetic and potential energy when doing IC engine first law analysis, or really when doing any type of combustion first law analysis. The change in energy due to heat and work transfer and the change in properties due to the chemical reaction itself are much, much greater than typically experienced changes in kinetic and potential energies. Okay, so we can take this differential form of the first law and we can integrate it between two states, right? So if you remember, thermodynamics is a state study, right? It's based on states. So you're going from some initial state to some final state, and you integrate this expression, this first law expression, through that process of going from state 1 to state 2, okay? So when you do that integration, you get that the integral of delta Q from state 1 to state 2 is Q1 to 2, and the integration of delta W through that process from state 1 to state 2 is work 1 to 2. The integral of du is just the change in internal energy between states 1 and state 2. So the right-hand side is delta U, which of course is the same as the internal energy at state 2 minus the internal energy at state 1. Now you'll notice the difference that we write the terms on the left-hand side versus the terms on the right-hand side. Both heat transfer and work transfer are what we call path or process functions. What that means is that the values of heat and work transfer depend on the path that's taken to get from one state to another state. The change in internal energy of the system itself, though, because internal energy is a property of a system, is just the difference in the energy values at those two states, U2 minus U1. Okay, what does that mean? Well, let's suppose that you went from state 1 to state 2, and you went along a certain path. Let's suppose it was a constant pressure process, right? So when we say it's a constant pressure process, what we're doing is we're imposing the type of process, we're imposing the path that the system takes in getting from state 1 to state 2. So you go from state 1 to state 2 along this constant pressure path, okay? And you correspondingly get to state 2, and you have a change in energy between state 1 and state 2, which is just U2 minus U1. And then knowing some other details of the process and knowing our first law equation, you'll be able to calculate the heat transfer between state 1 and state 2. Now let's suppose that rather than following a constant pressure process between state 1 and state 2, we follow some other process that allows us to go from state 1 to the exact same state 2, okay? Of course, we know that the pressure at state 1 and state 2 is the same because our first process was constant pressure, so we'd have to have some kind of process where perhaps we, slowly raise the pressure and then bring it back down and decrease it so that, at state 2, the pressure is the same as at state 1. It just followed a different path to get between the two states. Well, right away, you can kind of detect that your work transfer in doing that is going to be different. The change in internal energy, however, will be the same. So with the different work transfer, the heat transfer will also necessarily be different, right? In other words, they depend on the process or the path that's taken between these two states, whereas internal energy is a state property. Every system has energy at a given state, and the right-hand side is just saying that the change in energy of that system is the energy at state 2 minus the energy at state 1. Okay, so recognizing that this is total internal energy, so it's not mass specific, we can divide this by the mass and write our first law equation as Q1 to 2 minus work 1 to 2 equals mass times the change in specific internal energies between states 2 and 1. Okay, so I put a box around this equation because you're going to use this equation, or we're going to come back to this equation several times throughout this semester. So that's a good one to make a note of. Okay, so of course the other major type of system that we'll analyze this semester is what is called an open system. And an open system is our most general system, meaning it can exchange mass, energy, and entropy with the surroundings. Okay, so the way that we write an open system is we first of all recognize that the mass, energy, and entropy of the system could change with time. That's this dE by dt of the system. Okay. And we have heat transfer that we can exchange with the surroundings, and we can have work transfer that we can exchange with the surroundings. And because it's an open system, we also have the capability to flow mass in and out of the system, right? So we have mass in all from I equals 1 all the way up to I equals n, right? And likewise, we have mass that can flow out of the system, m dot e, where the E stands for exit, and we might have mass, we might have one mass leaving the system, or we may have m masses leaving the system. Okay. So everything here is actually the same that we have for the closed system. It's just that, first of all, it's written on a time basis, right? We typically do that because open systems are usually operating on a rate basis. In other words, things are operating per function of time. A good example is an engine, right? An engine is operating as a function of time. It's operating at a given rotational speed. The crankshaft is operating at a rotational speed, which of course is a time function. It's a time-dependent function, okay? So these three terms, W dot, dE by dt, and Q dot, are basically the same as the closed system, except that they're written on a time basis. And then, of course, the other major difference with the closed system is that we have mass flow in and out of the control system. Okay, so we can write our first law equation for this open system, and again, it's conservation of energy, right? So the change in energy of the control system has to be balanced by energy that flows in and out of the control system. So on the left-hand side, we have dE by dt, that's our change in energy of the system, and this is balanced by energy that flows in with heat transfer, and energy flow into the control system with mass flow rate, minus the work transfer out of the system, minus energy that flows out as a result of mass transfer leaving the control system. Now, one thing that you'll notice in the mass flux terms, the m dot I and the m dot E terms, is you'll notice that the mass flow rate is multiplied by enthalpy, not internal energy, right? Remember, H represents enthalpy, whereas U represents internal energy. This is a characteristic of energy that crosses a control surface, or mass that crosses a control surface. That mass has internal energy, it has a U term, but in order to flow that mass across the control surface, the surroundings has to apply a certain amount of work to get that to get that mass out of the surroundings and into the control system. And so anytime mass crosses a control system, not only does it have internal energy, U, but it also has that work term that's required to flow the mass from the surroundings to the system. And that's the PV part, right? Remember, enthalpy is internal energy plus PV, U plus PV. So the internal energy represents the energy that the mass inherently has, and the PV term represents the flow energy, what we call the flow work, to transfer the mass from the system into the surroundings. So anytime you have mass crossing a control surface, right, which is what we have in this case, this m dot I is mass that's coming from the surroundings, flowing into the control system. We use H, enthalpy, to describe its energy because it captures both the internal energy of that mass plus the flow work to get that mass into the control system. And likewise, we use enthalpy on the exit side for mass that's leaving the control system, where now, of course, the control system has to supply flow work to flow the mass from the system into the surroundings. Okay, so now this is basically one of the more general expressions for the first law that you'll see, okay? But for us, we like to simplify it a little bit further and recognize that in most of our applications of studying engines from a thermodynamics point of view, we'll actually be able to model the engine in a condition of what we call steady state, right? So steady state basically means that the system properties do not change with time. What are system properties? Well, things like temperature, pressure, specific volume, internal energy, enthalpy, entropy, these are all our system properties. So let me just go ahead and capture that because that's important to know. Right? So system properties are those parameters which characterize the state of a system, and example thermodynamic properties include energy, entropy, enthalpy, temperature, pressure, and specific volume. Now, technically, mass and volume are also properties of a system, but I usually try to reserve our discussions for intensive properties, what we call intensive properties. So just as a reminder, intensive properties are those, that are independent of mass, right? Independent of mass, or what we call mass specific. Okay, so when I say up here thermodynamic properties include energy, what I'll just go ahead and do is add in here the word specific on energy, entropy, enthalpy, and enthalpy, okay, because I already have it in front of volume. Temperature and pressure, of course, are both intensive properties, and specific volume, which is the volume of the system divided by the mass of the system, is therefore, of course, an intensive property, right? And just to remind you, since we've defined intensive, we might as well go ahead and define extensive. Extensive properties are those that are dependent on the mass. Okay, so examples of these are mass, of course, volume, and total internal energy, or big U, total enthalpy, or big H, and total entropy, or big S. Okay? Okay, so when we say that a system is operating steady state, what that means is that these properties, right, things like temperature, pressure, energy, entropy, mass, if you will, they're not changing with time, right? They're constant with time. If I observe my system at some instant in time, I'll record a temperature, pressure, energy, enthalpy, and entropy. And then if I step away and I come back some period of time later and I observe my system again, then if all those properties are exactly the same as my first measurement, then chances are the system has been operating in a steady state fashion. Okay? So additionally, when we say that a system is operating steady state, it also means that the inlet and exit properties are constant with time, and Q dot and W dot are constant with time. So when we look at our first law equation, what that's saying is that the properties of the system with time are not changing in steady state, so dE by dt is equal to 0. Q dot is constant with time, so even though this is a time-based function, it's not changing with time, right? In other words, there's no acceleration or deceleration, if you will, of heat transfer. Likewise, the enthalpy at the inlet is constant with time. It's always the same enthalpy as time goes on. M dot is constant with time, right? So even though there's a flow rate, it's flowing with time, it's flowing per unit time, that M dot is not changing with time, right? In other words, it's not accelerating or decelerating, if you will. Same is true with W dot, it's just a steady number, and the same is true with M dot E and HE. So when we make the steady state assumption, that allows us to write the first law equation as follows. Q dot, heat transfer, plus our energy flow in the form of mass flow rate, is equal to W dot plus the energy flow out that flows out with mass flow rate. Oftentimes you'll hear people say that the first law of thermodynamics is energy in equals energy out. That's not a perfectly universal or general statement, except for the specific case of it being open system operating in steady state. So on the left-hand side you have energy in, and on the right-hand side you have energy out. Okay, so as I mentioned, we already talked about this a little bit, but we have the term enthalpy in our first law equation, our open system first law equation, right? And it appears in the open system equation, but it usually does not appear in the closed system equation. There's one very specific case where you can use enthalpy nicely in a closed system first law equation, okay? But as I mentioned, enthalpy describes the energy of a flow, right? And in fact, it really only has physical meaning when a mass is flowing across a control surface. And like I said, there is one exception for this. But because enthalpy is composed of all properties, right? U plus PV is how we define enthalpy. Because it's completely composed of properties, it itself is also a property of a system, okay? So as I mentioned, energy is required to transfer mass between a system and surroundings, and we often call that energy flow work or flow energy. and it's represented by this term pressure times specific volume. So the flow also has internal energy. The mass of a flow has internal energy, and it could have kinetic energy and it could have potential energy. So we call the total energy of the flow, this little e sub flow, is composed of internal energy plus flow energy plus kinetic energy plus potential energy. And since these two terms consistently appear when describing the energy of a flow, and because every single variable in these two terms are properties, right? Internal energy is a property, pressure is a property, specific volume is a property, then we can in fact define a new property which we call enthalpy, which is just the combination of these three variables, internal energy plus pressure times the specific volume, okay? So that's why enthalpy is used, and that's why it appears in our first law equation. Okay, so for those of you that have had me for thermo, you know that I really can't talk about thermodynamics if we also don't have a discussion about the second law. And it has, of course, a lot of relevance for our thermodynamic analysis of internal combustion engines, and we'll see that become reality when we start doing some of our cycle analysis discussions with Chapter 3. So, in my opinion, okay, the second law is one of the most important and fundamental laws in physics and then engineering that we'll encounter. It really has applicability. What's very interesting about the second law is that it has applicability across all length and time scales of our physical world, right? In other words, when we talk about mechanics or when we talk about dynamics, we always have to caveat our discussion of dynamic systems or studying mechanics of a system to the, primarily the length scale of which we're doing our analysis, right? In other words, most of what we do in engineering is in what is called the classical realm or the Newtonian scale of physics, right? We can describe everything from the second law, Newton's second law of F equals ma, right? But if you start going to very large length scales like cosmic type length scales or very small length scales like nanoscale type length scales, then things like relativity and quantum physics start to take over and no longer allow us to apply those general Newtonian equations that we can apply in the classical length scales. Well, that's not true for the second law, or the first law, in fact, right? Energy is still conserved across all length and time scales, and more importantly, the second law is still applicable at all length and time scales, okay? So that's not why, though, I think it's one of the most important fundamental laws. The reason why I think it's one of the most important laws is because it really has the overarching effect of driving our natural processes in a given direction, right? So the most simple example that we can come up with is if you make your cup of coffee in the morning and you fill it, right? You fill your cup with nice hot coffee and you start to sip on it, and initially it's too hot to drink, so you wait a few minutes and naturally, of course, it gets a little cooler. And it doesn't take a mechanical engineering degree to understand why it's getting cooler, right? You have a heat transfer, that the coffee is hot, the room that it's in is cold. There's a delta T there, a temperature difference, and so we know, just based on our own physical experiences, that cup of coffee will cool down because it's in a cooler environment. It's in cooler surroundings, and the thermal energy will have a tendency to flow from high temperature to low temperature. But what may not be so obvious, or what we don't perhaps always extend our thinking to, is a thought experiment to say, well, what happens when the coffee is at room temperature, right? It's cooled down so much that now its thermal energy is exactly the same as the surroundings thermal energy, that is, they're both at the same temperature. When will the coffee heat back up, right? If I just leave that cup of coffee on the countertop, the question becomes, when will that coffee heat back up? Well, if you think about it strictly from a first law point of view, then there's actually no requirement that says that coffee cannot heat back up. All that the first law says is that the energy that was in the coffee flowed into the surroundings, and by the reckoning of the first law, that energy is in the surroundings So it should make perfect sense to allow that energy from the surroundings to flow back into the cup of coffee. The first law really doesn't care. So long as you don't create or destroy energy, the first law is perfectly happy. But of course, we know that we can sit there until the end of time waiting for our cup of coffee to heat back up, and it's never going to happen. Well, that's what the second law says. The second law basically is the law that captures that physical observation. The fact that the natural tendency, the spontaneous tendency, is for thermal energy to flow from hot to cold, and the reverse direction is impossible. The reverse direction of flowing from cold to hot is impossible. That would violate the second law of thermodynamics. That would, as we say, destroy entropy. And of course, many of you probably remember from your 315 days or your other thermodynamics courses that it was pounded into you that entropy cannot be destroyed, right? Entropy can only be created, and to say that energy flows from cold temperature to hot temperature would in fact be an example of how entropy would be being destroyed, okay? And that's of course impossible. And the reason why it's impossible is because you know that that's not something physical that you've ever observed or could ever observe, okay? Okay, so basically what I have written here is essentially what I just described to you in words, right? To get real fancy with the terminology, the second law of thermodynamics says that the net entropy of a system surrounding interaction will always increase, right? Or in the ideal case, the entropy can stay the same. The entropy interaction between the system and the surroundings can stay the same. It's this ideal case that we're going to talk a lot about in IC engines, right? This is what we use to help us fix some of our thermodynamic states when doing thermodynamic analysis of, say, a piston cylinder arrangement, okay? Okay, I also like to think of entropy and the second law in terms of the quality of energy, right? So if you think of work energy as being your highest quality energy, it's available to you to do something useful, right? You can use work energy to do something useful, and in other words, you can use work energy to move something. Well, that's very high quality, and it has no entropy, right? Entropy basically is an assessment of the lack of quality of energy. So if I have a unit of energy with low entropy, that is more useful to me than the same unit of energy that has high entropy, right? The more entropy that's in energy is less useful for me being able to do useful work with, okay? And another way to think about that is how ordered or disordered that energy is. Now, a lot of people will argue with me that using the words ordered and disordered are not the right words to use. And the reason why they don't like it is because it's not very precise, which is absolutely true, okay? But it still conceptually is nice to think of entropy as being basically the disordered component of energy. Something that's disordered cannot be put to use, right? It can't be put to useful work. And so, whereas something that is ordered can be put to useful work. And a good example is if you imagine the motion of a piston. Well, when a piston is, say during the expansion process of the engine, the combustion gases are forcing that piston down. Well, the piston is, all of the molecules of that piston are all going in the same direction, right? They're all moving in a direction, and because of that singular motion, that unidirection of all of those particles, they're able to transfer useful work, okay? So things that have entropy have a fraction of disordered energy, whereas things that don't have entropy do not have that fraction of disordered energy, okay? Okay, so just like we have a first law equation, we also have second law, process equations for open and closed systems, right? So if we're talking about a closed system second law equation, right? Basically that looks like the following. We say that the change in entropy of the control system, which is the entropy at state 2 minus the entropy at state 1, S2 minus S1, this is equal to the entropy that is added by heat transfer plus the entropy that is added due to generation. Okay, so if you remember back in our notes that I typed out, you remember that I said that, where did I say that? A closed system can also transfer entropy in the form of either heat transfer or entropy generation, right? So notice the two terms that are on the right-hand side of our entropy equation, heat transfer or entropy generation, okay? So the reason why this temperature is in the denominator of heat transfer is basically so that we have it's there to give that heat transfer a temperature reference point, okay? In other words, if you transfer thermal energy between a system and surroundings where the temperature is low, that's going to give you a higher entropy change than if your temperature were higher, okay? The entropy generation term is basically a destruction term of the usefulness of energy, okay? So remember that entropy is a quantification of the disorder or the uselessness that, a fraction of energy that may be present in energy, okay? So if I subject a system to a process, and that process started at an initial state having a certain capability to do useful work, but then at the end of the process, because of losses within the system, the availability of that energy to do useful work has decreased. Well, we capture the change in the usefulness of the work due to those losses in the system as this entropy generation term, okay? So we usually say that entropy generation quantifies the irreversibilities within a system. And irreversibilities is just a fancy word to say losses, right? So if you think about any losses that you have in a system, things like friction, right? Then that's going to be quantified in the entropy generation term. Okay, so that's our second law equation for a closed system. We also have the second law equation for an open system, which again looks very similar to our closed system equation, except we have two additional terms, right? We have, because it's an open system, the ability to transfer entropy with the mass flow in, and an ability to remove entropy from the system with the mass flow out, okay? So the left-hand side are our three entropy addition terms for the steady state open system, where we can add entropy in the form of heat transfer. You can also remove entropy with heat transfer, right? If the heat transfer is negative, if the thermal energy is flowing from the system to the surroundings, then this Q dot term will be negative, and you'll have an entropy flow out of the system. You can add entropy with the mass flow into the system, and you can add entropy due to generation, right? The irreversibilities or the losses within the system can basically create entropy within the system. And then, of course, that's all balanced by entropy that leaves the system, which, of course, would leave in the positive convention with a mass flow out of the system. Okay, so we've already spent some time talking about properties, right? We have various properties that characterize the system, such as temperature, pressure, specific volume, internal energy, enthalpy, and entropy. And what we didn't mention earlier is the fact that if we want to fix the state of a system, then we have to have no less, but we don't need more than, two independent properties, right? In other words, I have to have two independent properties in order to fix the state of the system. If I know two independent properties, then I can determine every other property of the system, every other thermodynamic property. Okay. Now there is a new word that we've added here in this dialogue, which is independent, right? And independent is not to be confused with intensive. Okay. So real quickly, we can just define that an independent property is one that can change irrespective of any other property. Okay? Most properties that we study are independent. By definition, independent properties must be intensive, right? i.e., they cannot be influenced by mass or the size of the system. Okay? And usually this is best done, the most common example This is usually best explained with the example of the most common example of non-independent or dependent, right? Are temperature and pressure during phase change, right? So for example, if water is changing phase from liquid to vapor, then temperature and pressure stay constant during that phase change process. And likewise, if you change the pressure or the temperature of water during a phase change, then you necessarily also change the other property, right? So if you change the pressure of water during phase change, then you've necessarily changed the temperature at which that phase change will occur, which of course is, in the case of going from liquid to vapor, is what we call the boiling temperature, right? So you all know that we can change the boiling temperature of water by changing the pressure of that water. Virtually all of the properties that we study in IC engines are going to be independent, right? So virtually all our properties in IC engines analysis, including temperature and pressure, are independent, okay? So you don't usually need to worry about that too much, except you do need to worry if I spell things correctly, which I've been known not to do. Okay, so that now leads us into the next big category of discussion that we need to know about, which is ideal gases, okay? So ideal gases, of course, are basically those which are composed of particles that behave independently relative to each other, okay? In other words, the particles are so spread out, that the gas has such a low density that the particles composing that gas really don't have any clue that there are other particles composing that gas, right? They don't interact with each other. The particles just behave independently, okay? What's important for us to note is that whenever we have an ideal gas, we can define its pressure, volume, and temperature relationship with the ubiquitous and famous ideal gas equation, right? In other words, pressure times specific volume is equal to the gas constant times temperature. And of course, if we want all of these units to work out nicely all the time, then we'll keep pressure in kPa, specific volume as cubic meter per kilogram. The gas constant is a gas-specific gas constant, so you have to look this value up for each gas that you are analyzing. It's not 8.314, in other words, it's not the universal gas constant. That has units of kilojoules per kilogram Kelvin. And then, of course, T is temperature with units of Kelvin, okay? Now, one of the other important definitions of an ideal gas, because the particles are independent, is that the change in energy of an ideal gas is only a function of temperature. All other substances, non-ideal gas substances, the change in energy of that substance is going to be a function of both temperature and pressure, okay? For ideal gases, though, internal energy and enthalpy are only functions of temperature. So what that means is if we remember our definition for the constant volume specific heat, what we call C sub V, okay? C sub V is fundamentally defined for all substances, not just ideal gases, all substances. It's fundamentally defined as the partial derivative of internal energy with respect to the partial of temperature while holding specific volume of that system constant. Now, the reason why internal energy has a partial differential in front of it is because, in general, internal energy is a function of more than just one property, okay? It's a function of temperature and pressure, for example, of the system, not just temperature. Likewise, the constant pressure specific heat, C sub P, is exactly defined as the partial of enthalpy with respect to temperature while holding pressure constant, okay? And again, enthalpy is a function of other properties of the system, not just one property, and so it's necessary to consider the multivariable nature of enthalpy when taking a derivative of it. In the case of ideal gases, though, energy, U, and enthalpy, H, are only functions of temperature. So we can drop these partial derivatives and write them as ordinary derivatives because u and h are only single variable functions. So we write that the constant pressure specific heat of an ideal gas is dH by dt along a line of constant pressure, not del H by del T along a line of constant pressure. Okay. Likewise, the constant volume specific heat for an ideal gas is written as du by dt, not del U by del T. Okay. And of course, because it's constant volume, then the change in internal energy with respect to temperature is taken along a line of constant volume. So the reason why this is important is because we can use these two definitions for Cp and Cv to calculate the change in enthalpy and change in internal energy of ideal gases. In other words, we can say that the change in enthalpy of an ideal gas is its constant pressure specific heat times its change in temperature, and the change in internal energy for an ideal gas is its constant volume specific heat times its change in temperature. Now, in order to determine delta H and delta U for an ideal gas, right, we would write an integral here and write an integral here. We have to know how constant pressure and constant volume specific heats change with temperature, okay? And without getting into infinite levels of detail about how Cp and Cv are functions of temperature for different gases, what we typically do, just to give ourselves what we would call a first order approximation, is assume that Cp and Cv are constant with temperature, okay? It's not precise, it's not accurate. A lot of gases have very strong functions of temperature. Their Cp and Cv values have very strong functions of temperature. But to do basically a first order approximation, or to get us within the ballpark, if you will, it's reasonable to assume constant values for Cp and Cv with temperature. So by doing that, now when we do this integration, because we're taking Cp and Cv to be constant with temperature, we can pull them out of the outside of the integration, and then we're just integrating dt. Okay, and so for changes in internal energy and enthalpy for ideal gases, we can say that H2 minus H1, or delta H, is equal to Cp delta T, and the change in internal energy, U2 minus U1, is equal to Cv delta T. Okay, you're going to want to put a box around these two equations because you're going to use these two equations frequently throughout the semester. Okay. Now, one important thing to note is that we can use these two equations to calculate the change in enthalpy or the change in internal energy, respectively, of ideal gases, regardless of the type of process, right? In other words, just because change in enthalpy is equal to Cp, constant pressure specific heat times change in pressure, does not mean that you have to have a constant pressure process to use this equation, okay? Likewise, you can use this equation, right? Or let me back up a minute. You can use delta U, for example, in a non-constant pressure or in a constant pressure process to calculate the change in internal energy, okay? What really matters is, what are you trying to understand, or what are you trying to calculate? Are you trying to calculate change in enthalpy? Then you can use Cp delta T regardless of what type of process it is, whether it's constant pressure or not. Likewise, if you're trying to calculate the constant volume specific heat, if you're trying to calculate the change in internal energy, then you can use Cv delta T regardless of the type of process, that is, if it's a constant volume process or not. Okay? Okay, so that's how you find change in energy and change in enthalpy. We also can find the change in entropy of an ideal gas, okay? And to do this, we rely on two general equations, which are called the TDS equations, or sometimes they're referred to as the Gibbs equations. I'm not going to go through the detailed derivations of these two TDS equations, nor am I going to go through the derivation of how you get from one of the TDS equations into the change in entropy expression. So that latter part is shown here for you. In terms of how you derive the TDS equations, it's pretty straightforward. You just basically do a first law analysis of a general system. It's not a big deal. But what the point is that if you use the first TDS equation, which is the following: TDS, temperature times the change in entropy, is equal to the change in internal energy plus the pressure times the change in volume. If you start with this equation, this then allows you to calculate the change in entropy of an ideal gas as follows. You can say that the change in entropy, delta S, is equal to the constant volume specific heat times the natural log of the temperature ratio between the two states, T2 over T1, plus the gas constant R times the natural log of the volume ratio between the two states, V2 over V1. Okay? Now, the one thing that I do want to mention with this expression is that it's assuming that the specific heats of the ideal gas are constant with temperature. Okay? And again, that's going to be a typical assumption that we make throughout our analysis of IC engines. When we do thermodynamic analysis, that'll be a very common assumption that we make. Constant volume and constant pressure specific heats are constant with temperature. And so this equation will be applicable for us throughout the semester. If instead I start with the second TDS equation, which is TDS is equal to dH minus VdP, then I come up with a second delta S, or change in entropy equation, which would give me the same change in entropy of the ideal gas, but just allows me to calculate it slightly differently. In other words, the second TDS equation allows me to calculate the change in entropy as delta S equal to Cp ln T2 over T1 minus R ln of P2 over P1. The choice of which equation we use depends on what information we have. If we know the pressures at the two states, then we would use this change in entropy equation. If we know the volumes between the two states, then we would use this delta S equation. Okay? Okay, so the next item that we want to discuss, okay, is understanding work transfer, right? So we discussed above how the first law equation relates changes in energy with work transfer and heat transfer, right? So I'm scrolling back up here to show where we have, for example, W dot, the work transfer for an open system, or work 1 to 2, W1 to 2, the work transfer for a closed system, okay? So we need to be able to calculate that work transfer for various situations that we will encounter with our piston cylinder arrangements in internal combustion engines. So for our purposes in IC engines, virtually all of our relevant work transfer is going to be in the form of the piston motion, right? That piston reciprocating up and down in the cylinder is basically changing the boundary of our control system, right? So if we say that the control system is that region that's trapped inside the cylinder between the piston and the cylinder head and the liners of the cylinder, then as that piston moves, what it's doing is it's changing its boundary, and the work associated with that motion is called boundary work, okay? So the general boundary work equation, which we've talked about in class already a little bit, is W equal to the integral of the pressure times the change in volume, dV, okay? Now we're going to evaluate this expression for a couple of different processes, right? So if you remember, I said that work and heat transfer can only occur during a process. That is, as a system goes from one state to a different state. And the first and second laws and the boundary work equations can be used to analyze any process, right? Doesn't matter which process it is. It doesn't matter if it's a reversible or an irreversible process. These first and second law equations and the boundary work equation, assuming that there is boundary work, can be used to analyze any of these processes, okay? There are a few special processes, though, that are particularly easy for us to analyze from particularly a boundary work point of view. So the first is what we call the constant volume process, right, for the closed system. So in this case, the change in volume is equal to 0. dV is equal to 0, and so our work transfer is equal to 0. So when we do the first law analysis, we have Q1 to 2 minus work 1 to 2 is equal to U2 minus U1. Because the volume is constant, there's no change in volume, the work transfer is equal to 0. And so the first law just tells us that the heat transfer is equal to U2 minus U1. And if we have an ideal gas with constant specific heats, then we can say that Q1 to 2 is equal to the mass times the constant volume specific heat times the temperature at state 2 minus the temperature at state 1. The next easy process to analyze is what we call the constant pressure process. And again, this is for a closed system. In the case of the constant pressure process, now pressure is constant, so we can pull it out of the integration and just integrate dV. So we get pressure times V2 minus V1. If we substitute that into the first law equation, we get that Q1 to 2 minus PV2 minus V1 equals U2 minus U1. And this right-hand side, because this is delta U, can be written as mass times constant volume specific heat times T2 minus T1. But there's also something else that's interesting, and that is if you notice that for an ideal gas, because PV equals MRT, we can say that P times V2 minus V1 is equal to MR T2 minus T1. And we can substitute that into our first law equation and get that Q1 to 2 minus MR T2 minus T1, that's the PV2 minus V1, is equal to MCV T2 minus T1. And now if we bring our like terms together, we can actually simplify this even further and eventually show that Q1 to 2 is equal to MCP T2 minus T1. Okay, but I just wanted to show you that relationship that you have with the ideal gas equation in terms of P V2 minus V1. The next type of special process is what we call the polytropic process. And the polytropic process is applicable to either a closed or an open system. Okay? In the case of how we mathematically describe a polytropic process, it's basically any process that is of the following form, where we say pressure times volume raised to this letter n, where n is called the polytropic index. This exponential product is equal to a constant for a polytropic process. Okay? So this is a really important expression for us in piston cylinder arrangements because the kinematic relationship between the crank arm, the crankshaft, and the piston, your linear slider, right, that linear motion of the slider to the rotational motion of the crank, basically causes the pressure inside the cylinder to behave as a function of volume according to this relationship. In other words, your compression and your expansion processes in an IC engine very closely follow a polytropic relationship. And so here, for example, I've drawn a compression curve, where as we decrease the volume, our pressure increases according to this curve here, and we can basically model this curve as a polytropic curve where PV to the n is equal to a constant. Okay, so how would we calculate the work transfer for that polytropic process? Well, we can say that the work transfer is equal to the integral of PdV, and since PV to the n is equal to a constant, we can do substitutions. We can do a lot of algebraic manipulation, and here's where we do our integration, and a little bit more algebra, and eventually get our work transfer term for that polytropic process to be of this form here. So the work transfer for a polytropic process when n does not equal 1 is P2V2 minus P1V1 divided by 1 minus n. If you happen to have a polytropic process where n equals 1, okay, this is actually a situation where you have what is called an isothermal process if it's an ideal gas. This would be the situation where there's an isothermal process. Then you just basically have to do your integration a little bit differently, and you'll get that the work transfer is equal to P1V1 times the natural log of V2 over V1. And of course, that's applicable for when n equals 1. Now, in both of these expressions, if we limit ourselves to ideal gases, then we can recognize, of course, that we have PVs in the terms, and so we can make the substitutions for RT, right? So that's what was done in this boxed equation here. We recognize that P times little v is equal to R times T of an ideal gas, and so you get that the gas constant times T2 minus the gas constant times T1, all divided by 1 minus n, is also equal to the work transfer term. And we did a similar substitution down here for the isothermal case for an ideal gas for the work transfer. Okay, now we have the last process that we want to talk about, which is what we call the ideal or the isentropic process. And this is a really important process for us in IC engines because it helps us establish the ideal extents with which our cycles, our thermodynamic cycles, will operate. Okay? So the way that we identify or define the ideal process is one which is what we call reversible and adiabatic. Okay? So you're going to hear these terms a lot this semester. Remember that reversible, what that means is that there is no entropy generation. Okay, a reversible process is one that has no losses. There's no entropy being generated, so we can say that the entropy generation, this S-gen term, is equal to 0. Likewise, an adiabatic process is one where there is no heat transfer, so Q is equal to 0. Okay? So if we look back on our second law equation, and if we say that the process is reversible, then the S-gen term is equal to 0. And if we say that the process is adiabatic, then the heat transfer term is equal to 0. So we get from the second law that the change in entropy of the system, ds, is equal to 0 for the reversible and adiabatic process, right? Which is what this is saying down here, ds is equal to 0. Okay? When we have that happen, when the entropy of a process stays constant, we give that the special name, which is called the isentropic process. Now, reflecting on our earlier equations that we developed way back up here, when we defined or determined the change in entropy of an ideal gas, right? Remember, we had these two equations for calculating the change in entropy of ideal gases. If we have an isentropic process, then that means that the delta S is equal to 0. So in both of these equations, the left-hand side would be equal to 0 for the isentropic process, for the reversible and adiabatic process. So using those two equations, we can come up with a set of very important relationships that are going to be very useful throughout this semester, which we call the isentropic relationships. Okay? So the background is we have an ideal gas. It's undergoing an isentropic process, meaning that it's a reversible and adiabatic process. And if we assume constant specific heats, then we can use our delta S equation from the TdS expression and basically manipulate this expression where delta S is equal to 0 for our isentropic process. And when we do that, algebraically, what we come up with is this expression here. The ratio of temperatures, T2 over T1, is equal to the inverse ratio of volumes, V1 over V2, raised to the gas constant divided by the constant volume specific heat, CV. We can simplify it further by recognizing that this gas constant R is just the difference between the constant pressure specific heat and the constant volume specific heat. Okay, now there's a very real reason why this relationship exists, but we're not going to be able to get into it this semester. You'll have to take 615 to learn what that relationship is. But we do define a ratio of the specific heats, and that ratio is called gamma. Okay, I often refer to it as gamma, but your thermodynamics textbook might refer to it as K. K and gamma are basically the same thing. They are the ratio of specific heats where Cp is in the numerator and Cv is in the denominator. So if I go through and I write, starting with this expression for R and this definition for gamma, I can show that R over Cv is equal to gamma minus 1. And so I can substitute that gamma minus 1 into my isentropic relationship for T2 over T1 and basically get this relationship that relates the temperature ratio between two states to the inverted volume ratios between those two states raised to gamma minus 1. We call this isentropic relationship number 1, and it's specific to an ideal gas undergoing an isentropic process with constant specific heats. Okay? Put a box around it because you're going to use this expression frequently this semester. If we start with the second TdS equation, we can basically come up with isentropic relationship number 2, which is the relationship or the ratio of the temperatures between the two states to the pressures between the two states. The difference, though, is you'll notice that the numerator, or excuse me, the exponent is gamma minus 1 divided by gamma, not just gamma minus 1, okay? And so whenever you have the temperature and pressure ratios, it's gamma minus 1 over gamma, okay? And again, this equation is appropriate for ideal gases undergoing an isentropic process assuming constant specific heats, okay? Finally, we can take our ideal gas equation and start with our second isentropic relationship and come up with a third isentropic relationship, which is the following. It's the pressure ratio related to the inverted volume ratio raised to the power of gamma, okay? And so this is isentropic relationship number 3. And again, this is appropriate only for ideal gases undergoing an isentropic relationship with constant specific heats. Okay, so what's interesting is if we take this relationship here and we multiply it out, right, what we'll get is P2V2 raised to the gamma is equal to P1V1 raised to the gamma, right? Or P times V raised to the gamma is equal to a constant. And what you'll notice is that is exactly the same form as our polytropic process. So an isentropic process is in fact a special type of polytropic process where N, the polytropic index, is equal to gamma, the ratio of specific heats. And what that further means is that all these equations that we developed for the isentropic relationship would also be applicable for the oh, you know what? I'm going to stop there. I need to be careful. I can't precisely say that. So pretend I didn't say that. What I want to point out is just that the isentropic process is a special type of polytropic process where PV to the N is equal to constant, and in the case of it being an isentropic process, N would be equal to gamma. Okay, so hope I didn't create any confusion there just a little bit ago, but if I did, just let me know, and I'll be happy to address any questions. Outside of that, have fun revisiting thermodynamics, and if you have any questions at all about any of the thermodynamic stuff, then please feel free to come visit with me. I'm more than happy to help you with it. Okay, have a good day, and I look forward to seeing you in class. Bye-bye.